Hello and welcome to our first video on Newton's universal law of gravitation. Okay, you might hear this referred to as in a few different ways. Universal law of gravitation usually works, or even just gravitation. Now, this might seem like kind of a funny unit to do right here, at least at the start, because you might be saying, wait a second, we already learned about gravity. We've already talked about how to find the force of gravity, but we've only looked at it in one specific situation. We have learned how to find the force of gravity that is acting on objects that are on Earth. And that's very useful for a lot of things that we want to do. Okay? We learned that the force of gravity equation, we also call force of gravity weight, by the way, is Fg equals mg, where m is the mass and g is the acceleration due to gravity in that location. That works great for objects that are on Earth. But what if we want to know the force of gravity for an object that isn't on Earth? Or what if we want to know the force of gravity between two objects and they're not anywhere near each other? For example, you might know that the Earth is gravitationally attracted to the Sun, but I wouldn't really consider the Sun to be on Earth or the Earth to be on the Sun. I don't think our 9.81 meters per second squared would be very useful there. Now we're going to move on and learn how to find the force of gravity between any two objects. Any objects with mass are gravitationally attracted to one another. So we're going to learn an equation that allows us to take any two objects and figure out what the force of gravity is between them. Not necessarily between the Earth and an object, but between just any two objects. And this is known, as you might have guessed, as the universal law of gravitation. And you, at this point, should have done a lab on this. And it turns out that there are three quantities that affect the force of gravity between two objects, that affect the size, how big it is. They are the following: the mass of the first object, m1, and then predictably the mass of the second object as well, m2. But the other thing that affects the force of gravity between any two objects is the distance between the centers of the masses. Okay, how far apart the centers of the masses are. And that's given by lowercase r. And when we did the lab, we saw how each of these quantities affected the force of gravity. It turned out that the force of gravity was proportional, or otherwise known as in a direct relationship, to either mass. If either mass changed by a certain factor, the force of gravity changed by the same factor. In other words, if we doubled one of the masses, then the force of gravity doubled. If we cut one of the masses, the same factor, not the same force. If we cut one of the masses so that it was only 1/3 the original size, then the force of gravity was cut to be 1/3 the original size. And we also saw that when we changed both masses by some factor, we had to take the product of the two factors of change. So if we doubled one mass and tripled the other, doubling is 2, tripling is times 3. We take 2 times 3 and we get 6. The new force of gravity should be 6 times as big. In terms of the distance between center of masses, we found that this is a much more complicated relationship. The force of gravity was inversely related to the square of the distance between the center of mass, the centers of each mass. And again, the symbol for that is r. Now that's a lot of words. Let me try and put it another way. In other words, if the distance changes by a certain factor, the force of gravity would change by the inverse or reciprocal of that factor squared. So on your lab, there was 2 examples that we specifically looked at. If we doubled the distance, it turned out that if we doubled the distance between the objects, the force was cut into, it was quartered. It was 1/4 the size that it originally was. And that makes sense because if you take the inverse of 2 and then you square that, the inverse of 2 is 1/2 and you square that is 1/4. Or if you want to do it the other way around, you double the distance. So we're going to square that factor. Squaring 2 is 4. Taking the inverse of that is 1/4. Likewise, when we cut the distance in half, if we square 1/2, we get 1/4. And if we take the inverse of that, we get 4. So if we halved the distance between the masses, then what ended up happening was that what ended up happening, if we halved the distance, the force was 4 times as great. So there's 2 parts that you have to remember to that, okay? The distance is inversely related, the force is inversely related to the square of the distance between the 2 objects, okay? You can't just take the inverse and you can't just square the distance. You have to do both of those things. And it should be noted that with the masses, bigger masses result in bigger force. For distance, bigger distance between the centers results in smaller force. We made some graphs on those labs as well, and those graphs looked more or less like this. Okay? The graph of the force of gravity versus one of the masses is linear. And the graph of the force of gravity versus the distance between the 2 objects looks not like a straight line going down, but like this. This is known as an inverse square law. So if you ever hear that phrase, inverse square law, it's literally talking about this type of relationship and this type of graph. So it's nice to know that the force of gravity is proportional to the mass and inversely proportional to the square of the distance between the masses. But it would be really nice if we can write one equation that kind of takes all that information and puts it all together. What we can do right now, before we do a little bit more work, is work on a proportionality between the force of gravity and these quantities. That would look something like this. Fg is proportional to m1. Remember, since there's 2 masses, it's m1 times m2, because we saw that we take the product of the 2 masses, of the factors of change for the 2 masses, and that can tell us how much the force of gravity changed by. Since we're going to put something down here, that's like an inverse, the inverse square of the distance between the centers. So we see that this tells us how Fg changes. If we increase the mass, or if we increase m1, if we change m1 by a certain factor, that's going to change Fg by a certain factor. If we change both m1 and m2, we take the products, and that's going to change Fg by a certain factor. If we change r by some factor, we have to square that factor and then take the inverse of it since it's on the bottom, and that will give us the factor change in Fg. But this isn't super useful to us yet because it's not an equation. If we want to write an equation, what we have to allow for is that there might be some constant, some coefficient that we have to stick on the front of this, this expression right here to make this a true equation. So we need to determine if there is a constant in the equation. The best way to do this is to assume that there might be. Okay, let's assume, I'm going to skip down here for just a second. Let's assume that we have this equation here. Fg equals, I'm going to just use capital G because that's what we actually use for this, m1 m2 over r squared. What we're doing is we're assuming that big G is some constant. It's some value that's always true, and that would make this equation accurate. Now, how would we go about finding what G is? Well, it would be really nice if, let's look at the factors here that we talked about, m1, m2, and r. What if we could get m1, m2, and r to somehow kind of cancel out, and then we'd be so that like the product of m1 and m2 is the exact same number as r squared. In other words, they just kind of go away because we would have the same thing on the top and the bottom. We'd be left with Fg equals G. Okay? We're not saying that Fg is equal to G. We're just saying if we were to set up m1, m2, and r in such a way, we could figure out the number, the value of this constant. So here's what we're going to do. We're going to set m1, m2, and r all equal to, now normally what I usually do is I set them all equal to 1 because 1 times 1 over 1 squared is just going to give us 1. However, they changed around the simulation on me. Okay, the simulation you guys use for the lab used to be really nice because I could just plug in 1s everywhere. Now I actually can't go lower than 10 kilograms, so that's really unfortunate. So we're going to set all these equal to 10 with whatever their units are. So they cancel out. Okay. So I'm going to go to my simulation. You see I have my simulation up here. I'm going to change the mass of M1 down to 10. I'm going to change the mass of M2 to 10. And I'm going to put them 10 meters apart. This is very useful because I have 0 and 10 right here. And now let's take a look at that force. 0.00000000067 newtons. Okay, let's remember that number. Okay. And before I finish this out, so they cancel out, and we see what Fg is equal to. And once we figure this out, I'm going to show you where in the reference tables you can actually go to look this up. Okay. So, if we set everything up the right way, here's what we end up with. Fg equals G, we're trying to solve for G right now, that constant, we're determining this constant's value, M1, M2 over R squared. If we set everything to equal, if we set M1, M2, and R all equal to 10, then remember F ended up being 0.00000000067. So if I want to write that in scientific notation, because that's way too many zeros, that would be, I'm moving at 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 spots. So that would be 6.7 times 10 to the negative 11th equals G, M1, M2. Oh, let me plug in for those, excuse me. We set with the mass to 10 kilograms, the other mass also to 10 kilograms, and R to 10 meters squared. Oh, and that 6.7 times 10 to the negative 11th, that was in newtons because it's a force. So here's what we end up with. We get 6.7, getting ahead of myself here, newtons equals G. I'm going to simplify this. Let's see, 10 kilograms times 10 kilograms is 100 kilograms squared times G over, let's see, this would be 100 meters squared. Now those values are going to cancel out, 100 and 100. The units we're not going to cancel out. We're going to bring the units to the other side. We end up with a value for G. I am just messing this up all over the place. I'm sorry, guys. 6.7 times 10 to the negative 11th newtons. We're going to bring the values to the other side. We're going to multiply the meters squared up top. We're going to divide by kilograms squared. We end up with our simulation telling us that this value for the constant is 6.7 times 10 to the negative 11th newtons times meters squared over kg squared. And that is what big G is equal to. Now, that's not actually exactly what big G is equal to. I can show you exactly what it's equal to here, but this is as good as the simulation can do for us. If you look at the very front of your reference tables, universal gravitational constant, big G, you've probably seen that a bunch of times. Right under it is acceleration due to gravity. Acceleration due to gravity is 9.81 meters per second squared. That's good for Earth. Big G, universal, means that this number is relevant all over the universe. 6.67, so you can see how we got 6.7 in our simulation, they just rounded up, times 10 to the negative 11th newtons, meters squared, over kilograms squared. So that's the number we're going to use. We're going to change this to 6.67 times 10 to the negative 11th newtons times meters squared over kg squared. Okay? It's actually this. And like we said, it is known as the universal gravitational constant. And the symbol for it is big G. So some of you have tried calling little g the gravitational constant beforehand. This is why I told you can't do that, okay? Because we already have a universal gravitational constant. We were just waiting until this unit to talk about it. Okay? So we finally have an equation. Fg equals big G times m1 times m2 over r squared. So if you want to know the force of gravity between any two objects, you simply look up the constant in the reference tables. It's never going to change. Plug in the masses of the objects and divide by the square of the distance between the centers of those objects. A couple more notes before we get to some examples. The force of gravity is always attractive. There's no such thing as repulsive gravity. Gravity does not repel objects, it attracts them. As long as objects have mass, we see that mass is important for this equation in terms of calculating the force. Any pair of objects will be attracted toward one another by the force of gravity. That doesn't mean other forces can't repel them, but gravity itself is always attracting objects together. It always wants to pull objects closer together. Okay, let's do some examples. Determine the magnitude of the force of gravity between two people of mass 65 kilograms who are standing 2 meters apart. We're going to write down our equation. Fg equals big G m1 m2 over r squared. Big G is 6.67 times 10 to the negative 11th newtons times meters squared over kilograms squared. And yes, you do have to write that every time. However, it's right in the reference tables. The units are right there for you, so no reason to mess that up. Two people that both have masses of 65 kilograms, so 65 kg times 65 kg, and they're standing 2 meters apart. So we do 2 meters, and we square that. Now, you do have to know how to type in scientific notation on your calculator at this point. Okay, it's really crucial that you know how to do this for this unit, because that number is you're going to have to type that in scientific notation every time. If you've got a calculator like mine, and actually most calculators have this button or something similar, it's up to you. You can go and look up how to do this if you don't have it on your own, if this isn't your exact calculator. If I want to type 6.67 times 10 to the negative 11th, there's a shortcut. I type in the beginning 6.67, I hit this EE button, and that brings up a little exponent, and I type in negative 11. EE stands for times 10 to the, so it replaces having to hit the multiply button, 10, and then the exponent. Please use this, okay? Don't waste your time typing in times 10 to the. Hit the EE button, it stands for times 10 to the, and then just type your scientific notation in. Times 65, divided by 2 squared is 4, and we get this, 0.00000007. So let's see, if I wanted to write that in scientific notation, 1, 2, 3, 4, 5, 6, 7, 8, I would have 7 times 10 to the negative 8th newtons. That's the force of gravity between those two people. Very, very small. Okay? The force of gravity between two people is very, very small, or between normal-sized objects, I guess we'll say. Why is the force of gravity between us and the Earth so much bigger? Well, it's because the Earth is a really big object. How does the force compare to the above if they stand 4 meters apart? You have two options with this question. You could either... Sorry, got lost in my train of thought for a second. So, you have a couple different options here. You could either do this whole thing again, type everything in again, and just change the r to 4 meters and then square that. Or, let's work on a little bit of algebra here. We're trying to figure out the value of a force that's new. We're trying to figure out the new value of this force if the people are farther apart. So I'm going to put Fg1 here as opposed to just regular Fg. Let's talk about what changes in this equation. G doesn't change. That's a gravitational constant. It's universal. That'll never change. We didn't say the masses of either of these people changed, so I'm still going to go with M1 and M2. But the distance apart did change. So I'm going to go with R1, 2. And how much different is R1 from just regular R? Well, they're standing 4 meters apart. They were standing 2 meters apart. So if this is R, then R1 must be equal to 2R. So watch what I'm going to do. G, M1, M2 over 2R squared. Instead of writing R1, I've substituted in 2R, and notice that I put that in parentheses, okay? Because it's crucially important that we use parentheses here. The squared part of this, we're squaring the entire denominator. We're not just squaring the r, we're also squaring the 2 here. That's really important. Once I write it like that, once I write it with parentheses, I'm going to change how it's written again. gm1, m2, and I'm going to square what's inside here, 2r. If I take 2r and I square it, I get 4r squared. And now I'm going to ask you to do a little bit of reasoning here. I want you to look at this part of what I have. gm1, m2 over r squared. Okay, we're going to leave the 4 out of it momentarily. gm1, m2 over r squared. Notice that that's the exact equation I had up here, gm1, m2 over r squared, and that's equal to fg. Because this is exactly equal to fg, I can write this like this. I have an extra 1/4 because the 4 is on the denominator, times fg. Okay, so what this is telling me is that the new force of gravity is 1/4 of the original. And does that make sense? It absolutely does, because originally we had, we doubled the distance, and if you remember what we talked about, when we double the distance, it's 1/4 of the force of gravity. So if I want to find the actual force of gravity, all I do is I take 1/4 times 7 times 10 to the -8 newtons. And I'm multiplying by 0.25. I end up with, let's see, 1, 2, 3, 4, 5, 6, 7, 8. 1.8 times 10 to the -8 newtons is the new force of gravity. You could do it the old way and plug in all the numbers, okay? Your issue there is that what if you make a mistake? What if you accidentally hit something wrong on your calculator? Could happen. There's not as much of a risk using this method. It's a little trickier to understand, but there's not as much risk to get it wrong if you do understand what we're doing here. So, you have two options. You can either figure out the numbers all over again, plug everything in again, or use this method. I will continue to use this method. Let's do a couple more. Let's calculate the force of gravity between the Earth and the Moon. We know that the force of gravity equation between two objects is given by g m1 m2 over r squared. We know that g from the reference tables is 6.67 times 10 to the -11th newtons times meters squared over kilograms squared. The masses of the moon and the mass of the Earth are actually given on your reference tables. Mass of the moon, 7.35 times 10 to the 22nd kilograms. Mass of the Earth, 5.98 times 10 to the 24th kilograms. And the distance between them, the mean distance, Earth to the moon, and by the way, this accounts for the center to center distance, so we're talking about the distance between their centers. The average distance between the Earth and the moon is 3.84 times 10 to the 8th meters. 3.84 times 10 to the 8th meters, and please don't forget that you need to square that. Let's see how big this force is. Again, you really need to understand how that EE button works, otherwise you're going to confuse yourself. 6.67 EE 10 to the -11th times 7.35 EE 22 times 5.98 EE 24 divided by, and here's what I like to do. Okay, you can do a couple different things here. You can do a whole bunch of different things actually. You could write this number out and put it like over here. Then take this number, square it, write it under that first number, and then just divide those two. If you don't want to do that, you can divide by parentheses 3.84 EE8, square it, end the parentheses, hit equals for 1.99 times 10 to the 20th newtons, or what I sometimes do if I don't want to use parentheses, is this just means we're dividing by this number twice. Divide by 3.84, 10 to the 8th. Divide by 3.84, 10 to the 8th. And we still get this. I'm going to cut this video off right here. We'll finish up in the next video on this note sheet, and we'll go and look at some more examples.